Hı. Tamam, ekran şey geliyorsa, düzgün geliyorsa. Ya burada şey arkadaşlar, sizden anlayacağınız, bazen böyle arada video serisi yapıyorduk. Birkaç tane aklımda olan vardı. Bu onlardan bir tanesi. Uzun bir video ama tek seferde bitmez. Yapabildiğimiz kadar. E, Bu Karpathy'nin anlatacak işte, yani bu ChatGPT vari şeyleri nasıl yapılıyor. Onları böyle güzel, basit bir dille anlatıyor. Ona başlayacağız şimdi. Biraz izleyelim, ara ara yorum yaparız. O arada dinlemek isteyen varsa. Biraz matematik içeriyor, biraz işte bu generative AI ile ilgili şeyler içeriyor. Onları birlikte bakacağız. Ben de sizle birlikte bakıyor olacağım. Yani bu arkadaşın daha önceki serilerini izlemiştim. Gayet güzel anlatıyor. Bakalım sizi nereye götürecek. Şöyle başladım. Ha, bir de ses geliyor mu gelmiyor mu onu söylersiniz bana. Uygulamanın sesi.
A comprehensive but general audience introduction to large language models like ChatGPT. And what I'm hoping to achieve in this video is to give you kind of mental models for thinking through what it is that this.
Şimdi durdurdum ama ses geliyor değil mi? Videonun sesi. Hı. Tamam, videonun sesi geliyorsa okey.
Tool is. It is obviously magical and amazing in some respects.
Şimdi burada bir detay geçeyim arkadaşlar. Yani evet, video İngilizce. Yani şey diyebilirsiniz, Türkçe. Yani artık öyle bir çağa geldik ki, yani ne yapıyorsanız bir şekilde İngilizce öğrenin bence. Ee, Yani artık her şeye global bakıyor olmak lazım. Belki 10 sene öncesinden evet, Türkçe dokümanlar, Türkçe kaynaklar bir şekilde kendi içimizde yoğruluyorduk ama artık devir öyle bir devire geldi ki içerik üretmek de hemen bir hafta sonrasında eskiyor, bir ay sonrasında eskiyor. O yüzden İngilizceyi falan bilmek her zaman iyidir. Aradaki terimleri kavrasanız bile olur. Ben arada dediğim gibi bir 10-15 dakikada bir yorum yaparım konuya. Onun haricinde de bakayım şeyde daha sonradan şeyin bir burada var mı? Yok. Burada bu arkadaş etkinleştirmemiş. Normalde şey vardır, ses dublaj vardır ama şey yapmamış, koymamış buna. Ya da subtitles deyip sadece İngilizce var yani. Şuradan options'a bir bakalım. Bu da real time çevirirse işimizi falan zorlaştırır. Neyse, böyle başlayalım biz. Teşekkür ediyorum herhangi birine. O zaman başlayalım.
It's really good at some things, not very good at other things, and there's also a lot of sharp edges to be aware of. So, what is behind this text box? You can put anything in there and press enter. But what should we be putting there? And what are these words generated back? How does this work? And what are you talking to exactly? So I'm hoping to get at all those topics in this video. We're going to go through the entire pipeline of how this stuff is built, but I'm going to keep everything sort of accessible to a general audience. So let's take a look at first how you build something like ChatGPT, and along the way, I'm going to talk about some of the sort of cognitive psychological implications of these tools. Okay, so let's build ChatGPT. So there's going to be multiple stages arranged sequentially. The first stage is called the pre-training stage. And the first step of the pre-training stage is to download and process the internet. Now, to get a sense of what this roughly looks like, I recommend looking at this URL here. So this company called Hugging Face collected and created and curated this data set called Fine Web. And they go into a lot of detail in this blog post on how they constructed the Fine Web dataset. And all of the major LLM providers like OpenAI, Anthropic, and Google, and so on, will have some equivalent internally of something like the Fine Web dataset. So roughly what are we trying to achieve here? We're trying to get a ton of text from the internet, from publicly available sources. So we're trying to have a huge quantity of very high quality documents. And we also want a very large diversity of documents because we want to have a lot of knowledge inside these models. So we want large diversity of high quality documents and we want many, many of them. And achieving this is quite complicated. And as you can see here, it takes multiple stages to do well. So let's take a look at what some of these stages look like in a bit. For now, I'd just like to note that, for example, the FineWeb dataset, which is fairly representative what you would see in a production-grade application, actually ends up being only about 44 terabytes of disk space. You can get a USB stick for like a terabyte.
Çok pardon arkadaşlar, şu paneli şeye alacağım. Biz burayı görüyorsunuz. Biz burayı görüyorsunuz. Bunu ekranda niye görmüyorum? Paneli de alayım bir saniye. Bunu kopyalayacağım. Kopyaladım. Şöyle tekrardan.
very easily. Or I think this could fit on a single hard drive almost today. So this is not a huge amount of data at the end of the day. Even though the internet is very, very large, we're working with text and we're also filtering it aggressively. So we end up with about 44 terabytes in this example. So let's take a look at kind of what this data looks like and what some of these stages also are. So the starting point for a lot of these efforts, and something that contributes most of the data by the end of it, is data from Common Crawl. So Common Crawl is an organization that has been basically scouring.
Burada şöyle bir detay geçelim. Burada şöyle bir detay geçelim. Şimdi bu mesela ChatGPT'yi nasıl yapıyorlarla alakalı bir içerik üreten bir abimiz. Daha önceden Tesla'da çalışmış. Bu konularda tecrübeli biri yani. E, Hugging Face'i zaten duymuşsunuzdur. Yani insanların böyle ne diyelim machine learning modellerinin Facebook gibi ya da GitHub'ı gibi düşünebilirsiniz. İnsanlar oraya eğittikleri modelleri koyuyorlar. Daha sonradan community'den orada yorum yapıyorlar, işte puan veriyorlar falan. Daha çok fazla özelliği var da bu modellerle ilgili çalıştığınız zaman acaba şu işi yapan başka bir model var mı önceden dediğinizde Hugging Face'e bakıyorsunuz çoğu zaman. Burada da hani bir şey eğiteceksiniz. Eğitirken elinizde data olması lazım. İşte o datadan bahsediyor. Fine Web diye bir kavram var. İnternette hani çok fazla zararlı içerik falan da var ya. Onları böyle filtrelemiş şekilde daha böyle elle tutulur faydalı bilgileri toplamış bir kuruluş gibi düşünebilirsiniz. Onu üreten bir organizasyon var. Common Crawl. Ve 44 terabaytlık bir şey var, veri var orada. Onun üzerinden bazı işlemeleri kendiniz yapabiliyorsunuz. Aslında anlattığı o. Başlangıç noktası buydu. Şimdi devam edelim.
The internet since 2007. So as of 2024, for example, Common Crawl has indexed 2.7 billion web pages, and they have all these crawlers going around the internet. And what you end up doing basically is you start with a few seed web pages, and then you follow all the links. And you just keep following the links, and you keep indexing all the information, and you end up with a ton of data of the internet over time. So this is usually the starting point for a lot of these efforts. Now, this Common Crawl data is quite raw and is filtered in many, many different ways. So here they document, this is the same diagram, they document a little bit the kind of processing that happens in these stages. So the first thing here is something called URL filtering. So what that is referring to is that there's these block lists of basically URLs that are, or domains that you don't want to be getting data from. So usually this includes things like malware websites, spam websites, marketing websites, racist websites, adult sites, and things like that. So there's a ton of different types of websites that are just eliminated at this stage because we don't want them in our data set. The second part is text extraction. You have to remember that all of these web pages, this is the raw HTML of these web pages that is being saved by these crawlers. So when I go to inspect here, this is what the raw HTML actually looks like. You'll notice that it's got all this markup, like lists and stuff like that, and there's CSS and all this kind of stuff. So this is computer code almost for these web pages. But what we really want is we just want this text, right? We just want the text of this web page, and we don't want the navigation and things like that. So there's a lot of filtering and processing and heuristics that go into adequately filtering for just the good content of these web pages. The next stage here is language filtering. So for example, FineWeb filters using a language classifier. They try to guess what language every single web page is in, and then they only keep web pages that have more than 65% of English, as an example. And so you can get a sense that this is like a design decision that different companies can take for themselves. What fraction of all different types of languages are we going to include in our data set? Because, for example, if we filter out all of the Spanish, as an example, then you might imagine that our model later will not be very good at Spanish because it's just never seen that much data of that language. And so different companies can focus on multilingual performance to a different degree, as an example. So FineWeb is quite focused on English. And so their language model, if they end up training one later, will be very good at English, but not maybe very good at other languages. After language filtering, there's a few other filtering steps and deduplication and things like that. Finishing with, for example, the PII removal. This is personally identifiable information. So as an example, addresses, social security numbers, and things like that, you would try to detect them and you would try to filter out those kinds of web pages from the data set as well. So there's a lot of stages here, and I won't go into full detail, but it is a fairly extensive part of the pre-processing, and you end up with, for example, the FineWeb dataset. So when you click in on it, you can see some examples here of what this actually ends up looking like, and anyone can download this on the Hugging Face webpage. And so here's some examples of the final text that ends up in the training set. So this is some article about tornadoes in 2012. So there's some tornadoes in 2012 and what happened. This next one is something about, did you know you have two little yellow 9-volt battery-sized adrenal glands in your body? Okay, so this is some kind of a odd medical article. So just think of these as basically web pages on the internet filtered just for the text in various ways. And now we have a ton of text, 40 terabytes of it. And that now is the starting point for the next step of this stage. Now, I wanted to give you an intuitive sense of where we are right now. So I took the first 200 web pages here, and remember we have tons of them, and I just take all that text and I just put it all together, concatenate it. And so this is what we end up with. We just get this just raw text, raw internet text. And there's a ton of it, even in these 200 web pages. So I can continue zooming out here. And we just have this like massive tapestry of text data. And this text data has all these patterns. And what we want to do now is we want to start training neural networks on this data so the neural networks can internalize and model how this text flows, right? So we just have this giant texture of text. And now we want to get neural nets that mimic it. Okay, now before we plug text into neural networks, we have to decide how we're going to represent this text and how we're going to feed it in. Now, the way our technology works for these neural nets is that they expect a one-dimensional sequence of symbols, and they want a finite set of symbols that are possible. And so we have to decide what are the symbols, and then we have to represent our data as a one-dimensional sequence of those symbols. So right now what we have is a one-dimensional sequence of text. It starts here and it goes here and then it comes here, etc. So this is a one-dimensional sequence, even though on my monitor, of course, it's laid out in a two-dimensional way, but it goes from left to right and top to bottom, right? So it's a one-dimensional sequence of text. Now, this being computers, of course, there's an underlying representation here. So if I do what's called UTF-8 encode this text, then I can get the raw bits that correspond to this text in the computer. And that's what that looks like this. So it turns out that, for example, this very first bar here is the first 8 bits as an example. So what is this thing, right? This is a representation that we are looking for in a certain sense. We have exactly two possible symbols, 0 and 1, and we have a very long sequence of it, right? Now, as it turns out, this sequence length is actually going to be a very finite and precious resource in our neural network. And we actually don't want extremely long sequences of just two symbols. Instead, what we want is we want to trade off this symbol size of this vocabulary, as we call it, and the resulting sequence length. So we don't want just two symbols and extremely long sequences. We're going to want more symbols and shorter sequences. Okay, so one naive way of compressing or decreasing the length of our sequence here is to basically consider some group of consecutive bits, for example, 8 bits, and group them into a single what's called byte. So because these bits are either on or off, if we take a group of 8 of them, there turns out to be only 256 possible combinations of how these bits could be on or off. And so therefore we can re-represent this sequence into a sequence of bytes instead. So this sequence of bytes will be 8 times shorter, but now we have 256 possible symbols. So every number here goes from 0 to 255. Now I really encourage you to think of these not as numbers, but
10 dakikada bir yorumlayacağız demiştik. Onu şey yapalım kaçırmadan. Burada
as unique.
şeyden bahsediyor. Bizim ChatGPT'ye bir şey soruyorsun, sana cevap veriyor ya. Nasıl anlıyor onu? Çünkü arkada çalışan model eğitilmiş. Ona göre eğitilmiş. Burada Fine Web'den bahsetti. Elimizde Fine Web'in sağladığı bir tane veri seti var anlattığı. Hugging Face'te gösterdiği mesela ilk 5 GB'ı gösteriyordu. 5 GB'ın içinde sayfalandırmaya baktınız mı bilmiyorum. 288 milyon bilmem kaç son sayfa numarası. Yani o 5 GB'lık data Fine Web'den alınmış, değişik kaynaklardan içeren raw text diyor. O sadece 5 GB ama 44 terabayt var. Yani 1024 GB'ı 1 terabayt hesaplayın işte. Yani o datanın kat kat daha fazlası. Onu yaparken de işte ne yapıyor? URL filtering, text extraction, yani herhangi bir web sayfasındaki sadece faydalı olan kısımları alıyor. İşte o reklam kodlarını, navigasyonu, header menü falan onları değil de asıl içerik neyse önemli olan orayı çıkartıyor. Tabii onun bir algoritması var. Heuristiklerden falan bahsetti. Onun için muhtemelen böyle bir şey yapmak istesek orada bir common crawl'dan falan bahsetmişti. O onu yapabiliyor. Language filtering var. Fine Web'in şu anda yaptığı sadece İngilizce üzerine yoğunlaşıyor. Diğer dillerde garanti vermiyor sana. O yüzden sen mesela İspanyolca falan bir makale varsa sistemde orada biraz sapıtabilir den bahsediyor. Tabii deduplication'ları şey yapması lazım. Yani birbirini kopyalamış kaynaklar varsa onları da çıkartıyor olmak lazım. Yani internette her şey, örnek veriyorum, %50'si kopyaysa, sadece örnek veriyorum, 44 terabaytlık data aslında 22 terabayta düşürülebilir. O yüzden deduplication'ın önemi var. Veriyi olabildiğince tutarlı ve öz tutmak gerekiyor. Custom filtre, senin koyabileceğin filtre. Bir de PII'den bahsetti. Personal Identifiable Information diye bir şey vardı. Yani böyle kişilerin adres bilgileri, sigorta numaraları falan, onları da çıkartıyor olman lazım. Bunu yaptıktan sonra şeyden bahsediyor. Elinde bir veri var. Bu veriyi gösterebiliyor olman lazım. Gösterebilmek için de onu tokenize etmen gerekiyor diyor. Yani aslında tokenize sembolden bahsediyor burada. Sembolleri yan yana dizdiğin zaman da sequence'ları oluşturuyor. İlk başta sembollerde şeyden bahsetti. Yani sen bir yazı okuyorsun ama oradaki her bir karakterin arkada bir karşılığı var değil mi? Yani ASCII table'ı hatırlayın. Onlar 8 bitlik ifadelerle bir karaktere tekabül ediyor. Orada örnekte 0001 diye gidiyor. Bu bayağı bir uzun sequence olacak, dizilim olacak bununla. Bunu kısaltabiliyorsak güzel bir şey. O yüzden bit vermeyelim de 8 bit verelim. Ona da bir byte diyelim dediler. Ama şimdi ilk durumda iki seçeneğim vardı. Ya 0 olabilirdi ya 1 olabilirdi. Onların birleşiminden de upuzun bir sekans, dizilim. Ama byte'a çıkardığın zaman evet 124, 86 kaçta birine düşmüş oldu? 8'de birine. Çünkü önceden 8 tane karakterim vardı. Şimdi onu 1 byte'a indirdin. Yani teke indirdin. Veri setin 8'de biri küçülmüş olabilir. Ama bu sefer de içindeki sembol varyasyonunu arttırmış oldum. Önceden 0 ve 1 vardı. Şu anda byte'a çevirdiğin için 258'den 256 tane varyasyonum var. Yani sequence'ı küçülttükçe varyasyonu artmış oluyor. Sembol varyasyonu. Ondan bahsediyor. Bu tokenizing önemli burada. Hatta şimdi oraya da gelecek mi bilmiyorum ama bundan sonrasında bir devam edelim bakalım ne diyecek.
IDs, or like unique symbols. So maybe it's a bit more, maybe it's better to actually think of these, to replace every one of these with a unique emoji. You'd get something like this. So we basically have a sequence of emojis, and there's 256 possible emojis. You can think of it that way. Now, it turns out that in production for state-of-the-art language models, you actually want to go even beyond this. You want to continue to shrink the length of the sequence because, again, it is a precious resource in return for more symbols in your vocabulary. And the way this is done by running what's called the byte pair encoding algorithm. And the way this works is we're basically looking for consecutive bytes or symbols that are very common. So for example, it turns out that the sequence 116 followed by 32 is quite common and occurs very frequently. So what we're going to do is we're going to group this pair into a new symbol. So we're going to mint a symbol with an ID 256, and we're going to rewrite every single pair 11632 with this new symbol. And then we can iterate this algorithm as many times as we wish. And each time when we mint a new symbol, we're decreasing the length and we're increasing the symbol size. And in practice, it turns out that a pretty good setting of basically the vocabulary size turns out to be about 100,000 possible symbols. So in particular, GPT-4 uses 100,277 symbols. And this process of converting from raw text into these symbols, or as we call them, tokens, is the process called tokenization. So let's now take a look at how GPT-4 performs tokenization, converting from text to tokens and from tokens back to text, and what this actually looks like. So one website I like to use to explore these token representations is called TikTokenizer. And so come here to the dropdown and select CL100K base, which is the GPT-4 base model tokenizer. And here on the left, you can put in text, and it shows you the tokenization of that text. So for example, hello space world. So hello world turns out to be exactly two tokens. The token hello, which is the token with ID 15,339, and the token space world, that is the token 1917. So hello space world. Now, if I was to join these two, for example, I'm going to get, again, two tokens, but it's the token H followed by the token hello world without the H. If I put in two spaces here between hello and world, it's again a different tokenization. There's a new token 220 here. Okay, so you can play with this and see what happens here. Also keep in mind, this is not, this is case sensitive. So if this is a capital H, it is something else. Or if it's hello world, then actually this ends up being 3 tokens instead of just 2 tokens. Yeah, so you can play with this and get sort of like an intuitive sense of what these tokens work like. We're actually going to loop around to tokenization a bit later in the video. For now, I just wanted to show you the website, and I wanted to show you that this text basically, at the end of the day, so for example, if I take one line here, this is what GPT-4 will see it as. So this text will be a sequence of length 62. This is the sequence here. And this is how the chunks of text correspond to these symbols. And again, there's 100,277 possible symbols, and we now have one-dimensional sequences of those symbols. So yeah, we're going to come back to tokenization, but that's for now where we are. Okay, so what I've done now is I've taken this sequence of text that we have here in the dataset, and I have re-represented it using our tokenizer into a sequence of tokens. And this is what that looks like now. So for example, when we go back to the FineWeb dataset, they mentioned that not only is this 44 terabytes of disk space, but this is about a 15 trillion token sequence of in this dataset. And so here, these are just some of the first 1 or 2 or 3 or a few thousand here, I think, tokens of this data set, but there's 15 trillion here to keep in mind. And again, keep in mind one more time that all of these represent little text chunks. They're all just like atoms of these sequences, and the numbers here don't make any sense. They're just unique IDs. Okay. So now we get to the fun part, which is the neural network training. And this is where a lot of the heavy lifting happens computationally when you're training these neural networks. So what we do here in this step is we want to model the statistical relationships of how these tokens follow each other in the sequence. So what we do is we come into the data and we take windows of tokens. So we take a window of tokens from this data fairly randomly, and the window's length can range anywhere between 0 tokens, actually, all the way up to some maximum size that we decide on. So for example, in practice, you could see a token windows of, say, 8,000 tokens. Now, in principle, we can use arbitrary window lengths of tokens, but processing very long, window sequences would just be very computationally expensive. So we just kind of decide that, say, 8,000 is a good number, or 4,000 or 16,000, and we crop it there. Now, in this example, I'm going to be taking the first 4 tokens, just so everything fits nicely. So these tokens, we're going to take a window of 4 tokens, this bar, view, ing, and space single, which are these token IDs. And now what we're trying to do here is we're trying to basically predict the token that comes next in the sequence. So 3962 comes next, right? So what we do now here is that we call this the context. These 4 tokens are context, and they feed into a neural network. And this is the input to the neural network. Now, I'm going to go into the detail of what's inside this neural network in a little bit. For now, what's important to understand is the input and the output of the neural net. So the input are sequences of tokens of variable length, anywhere between 0 and some maximum size, like 8,000. The output now is a prediction for what comes next. So because our vocabulary has 100,277 possible tokens, the neural network is going to output exactly that many numbers, and all of those numbers correspond to the probability of that token as coming next in the sequence. So it's making guesses about what comes next. In the beginning, this neural network is randomly initialized. So, and we're going to see in a little bit what that means, but it's a random transformation. So these probabilities in the very beginning of the training are also going to be kind of random. So here I have 3 examples, but keep in mind that there's 100,000 numbers here. So the probability of this token, space direction, the neural network is saying that this is 4% likely right now. 11799 is 2%. And then here, the probability of 3962, which is post, is 3%. Now, of course, we've sampled this window from our data set, so we know what comes next. We know, and that's the label, we know that the correct answer is this 3962 actually comes next in the sequence. So now what we have is this mathematical process for doing an update to the neural network. We have a way of tuning it, and we're going to go into a little bit of detail in a bit. But basically, we know that this probability here of 3%, we want this probability to be higher, and we want the probabilities of all the other tokens to be lower. And so we have a way of mathematically calculating how to adjust and update the neural network so that the correct answer has a slightly higher probability. So if I do an update to the neural network now, the next time I feed this particular sequence of 4 tokens into the neural network, the neural network will be slightly adjusted now, and it will say, okay, post is maybe 4%, and case now maybe is 1%, and direction could become 2% or something like that. And so we have a way of nudging, of slightly updating the neural net to basically give a higher probability to the correct token that comes next in the sequence. And now you just have to remember that this process happens not just for this token here, where these 4 fed in and predicted this one. This process happens at the same time for all of these tokens in the entire data set. And so in practice, we sampled little windows, little batches of windows, and then at every single one of these tokens, we want to adjust our neural network so that the probability of that token becomes slightly higher. And this all happens in parallel in large batches of these tokens. And this is the process of training the neural network. It's a sequence of updating it so that its predictions match up the statistics of what actually happens in your training set. And its probabilities become consistent with the statistical patterns of how these tokens follow each other in the data. So let's now briefly get into the internals of these neural networks just to give you a sense of what's inside. So
Gerçekten o Tokenizer diye bir uygulama var. Sen mesela harcıyorsun ya, ChatGPT diyor sana şu kadar input token, şu kadar output token diye. İşte sen o yazdığın sorular onları alıyor, tokenize ediyor. Kaç tane token olduğu içeriden çıkıyor. Sonra sen diyorsun ki milyonlarca token harcadım. Halbuki o kelimelerin içinden çıkarıldığı için öyle bir hesaplaması var. E, Nasıl tokenize ettiği kullandığı modele göre değişebiliyor. Orada C-Base diye bir şeyden bahsetti. ChatGPT'nin kullandığı. Gerçi burada ChatGPT 4 diyor. 11 ay oldu. Yenilerinde belki değişmiştir. Ama nihayetinde bu bir model olduğu için, model eğitildiği için böyle cümleler, kelimeler falan değil de arka tarafında kullandığın token ID'si. Hani mesela byte'lardan bahsetmiştik ya, ilk 0-1'lerden bahsetmişti. Sonra 0-1 olunca iki varyasyon var ama sequence çok uzun oluyor demişti. O yüzden onu küçültmen lazım. Yani varyasyonlar artacak bu sefer. Yani mesela bitten byte'a çıkardığında şey gibi geliyor sana. Veri setinde sanki 8'de 1'ine düşüyor ama bir byte'da da 256 tane seçeneğin oluyor bu sefer. Nihai hedefin şey olması gerekiyor diyor. Veri seti devamlı varyasyonları arttırıp sekünsi daha küçültüyor olman lazım dedi. Burada da şeyden bahsetti kısaca. Şimdi detaylarına girecek de bu neural network kısmından bahsetti. Neural net'i eğitmeden bahsetti. Elinde bir tane şey var. Context window'u var. Şeylerin, tokenlar yan yana gelerek konteksti oluşturuyor ki şeyi de hatırlayın. ChatGPT'de falan da yazarken context window'un bir limiti var. Context limiti var. Onu aşamıyorsun yazarken. Burada da aynı. Tokenları yan yana getiriyorsun, konteksti oluşturuyorsun. Diyor ki bunu neural network'a sokuyorsun. Soktuktan sonra karşılığında kaç tane olası seçenek var, kaç tane token gelebilir diyor. Bu bir şey istatistiksel hesaplama. Tamamen istatistiksel hesaplama. Orada mesela şeyden bahsetti. 100.277 tane token olasılığı var. Ama bu bir seferlik bir şey değil. Bu hesaplamayı devamlı yapılıyor ve o numaralar değişiyor. Ne kadar eğittikten sonra da o probabilistik olan sayılar daha gerçekçi olmaya başlıyor. Ve sen bir şey yazdığında onun tamamladığı ya da sen bir soru sorduğunda sana verdiği cevap aslında o neural net'ten eğitildikten sonra bilebildiği kısımlar oluyor. Şimdi bu neural net'in iç yapısını biraz şey yapacak, detaylandıracak ona bakalım. 30. dakikada bir yorum daha yaparız.
neural network internals. So as I mentioned, we have these inputs that are sequences of tokens. In this case, this is 4 input tokens, but this can be anywhere between 0 up to, let's say, 1,000 tokens. In principle, this can be an infinite number of tokens. It would just be too computationally expensive to process an infinite number of tokens. So we just crop it at a certain length, and that becomes the maximum context length of that model. Now, these inputs X are mixed up in a giant mathematical expression together with the parameters or the weights of these neural networks. So here I'm showing 6 example parameters and their setting, but in practice, these modern neural networks will have billions of these parameters. And in the beginning, these parameters are completely randomly set. Now, with a random setting of parameters, you might expect that this this neural network would make random predictions, and it does. In the beginning, it's totally random predictions. But it's through this process of iteratively updating.
Ben burada böleyim de şey atladım. İlk train'in ilk başlarında bazı şeyler tamamen random gelebilir diyor cevaplar. Bu normal. Eğittikçe daha güzel cevaplar veriyor. Şeyi sadece tahmin ediyorum. Belki kumrunun başına gelmiş olan bu olabilir. Hani biraz saçma cevaplar veriyor olması. Şey demişlerdi evet. Da farklı alanlara yönelmiş bir model demişti. Demişlerdi daha doğrusu. Olabilir ama çok temel şeyleri. Yani 2 artı 2'yi 5 söylemesi herhalde olmaması gerekiyordu öyle bir şey. 2 artı 2'nin 5 olması gibi. Ya da çok basit sorulara cevap verememesi gibi. 2 artı 2'ye 5 diyen mesela örnek veriyorum. Hukukla ilgili bir LLM modeli diyelim bunu. Herhalde orada da yanlış yapar diye düşünüyorum. Ben çok basit şeylerde hata yapıyordum. Devam edelim.
The network, and we call that process training a neural network, so that the setting of these parameters gets adjusted such that the outputs of our neural network becomes consistent with the patterns seen in our training set. So think of these parameters as kind of like knobs on a DJ set. And as you're twiddling these knobs, you're getting different predictions for every possible token sequence input. And training a neural network just means discovering a setting of parameters that seems to be consistent with the statistics of the training set. Now, let me just give you an example of what this giant mathematical expression looks like, just to give you a sense. And modern networks are massive expressions with trillions of terms probably. But let me just show you a simple example here. It would look something like this. I mean, these are the kinds of expressions, just to show you that it's not very scary. We have inputs x, like x1, x2, in this case, 2 example inputs, and they get mixed up with the weights of the network, w0, w1, 2, 3, etc. And this mixing is simple things like multiplication, addition, exponentiation, division, etc. And it is the subject of neural network architecture research to design effective mathematical expressions that have a lot of kind of convenient characteristics. They are expressive, they're optimizable, they're parallelizable, etc. And so, but at the end of the day, these are not complex expressions, and basically they mix up the inputs with the parameters to make predictions, and we're optimizing the parameters of this neural network so that the predictions come out consistent with the training set. Now, I would like to show you an actual production grade example of what these neural networks look like. So for that, I encourage you to go to this website that has a very nice visualization of one of these networks. So this is what you will find on this website. And this neural network here that is used site that has a
Net. BB'yi drop. BB. Ha. Tamam. Size de göndereyim.
very nice visualization of one of these networks. So this is what you will find on this website. And this neural network here that is used in production settings has this special kind of structure. This network is called the transformer. And this particular one, as an example, has 85,000 roughly parameters. Now, here on the top, we take the inputs, which are the token sequences. And then information flows through the neural network until the output, which here are the logit softmax, but these are the predictions for what comes next, what token comes next. And then here, there's a sequence of transformations and all these intermediate values that get produced inside this mathematical expression as it is sort of predicting what comes next. So as an example, these tokens are embedded into kind of like this distributed representation, as it's called. So every possible token has kind of like a vector that represents it inside the neural network. So first we embed the tokens, and then those values kind of like flow through this diagram. And these are all very simple mathematical expressions individually. So we have layer norms and matrix multiplications and softmaxes and so on. So here's kind of like the attention block of this transformer. And then information kind of flows through into the multi-layer perceptron block and so on. And all these numbers here, these are the intermediate values of the expression. And you can almost think of these as kind of like the firing rates of these synthetic neurons. But I would caution you to not kind of think of it too much like neurons, because these are extremely simple neurons compared to the neurons you would find in your brain. Your biological neurons are very complex dynamical processes that have memory and so on. There's no memory in this expression. It's a fixed mathematical expression from input to output with no memory. It's just a stateless. So these are very simple neurons in comparison to biological neurons, but you can still kind of loosely think of this as like a synthetic piece of brain tissue, if you like to think about it that way. So information flows through, all these neurons fire until we get to the predictions. Now, I'm not actually going to dwell too much on the precise kind of like mathematical details of all these transformations. Honestly, I don't think it's that important to get into. What's really important to understand is that this is a mathematical function. It is parametrized by some fixed set of parameters, like say 85,000 of them. And it is a way of transforming inputs into outputs. And as we twiddle the parameters, we are getting different kinds of predictions. And then we need to find a good setting of these parameters so that the predictions sort of match up with the patterns seen in the training set. So that's the transformer. Okay, so I've shown you the internals of the neural network, and we talked a bit about the process of training it. I want to cover one more major stage of working with these networks, and that is the stage called inference. So in inference, what we're doing is we're generating new data from the model. And so we want to basically see what kind of patterns it has internalized in the parameters of its network. So to generate from the model is relatively straightforward. We start with some tokens that are basically your prefix, like what you want to start with. So say we want to start with the token 91. Well, we feed it into the network. And remember that the network gives us probabilities, right? It gives us this probability vector here. So what we can do now is we can basically flip a biased coin. So we can sample basically a token based on this probability distribution. So the tokens that are given high probability by the model are more likely to be sampled when you flip this biased coin. You can think of it that way. So we sample from the distribution to get a single unique token. So for example, token 860 comes next. So 860 in this case, when we're generating from model, could come next. Now 860 is a relatively likely token. It might not be the only possible token in this case. There could be many other tokens that could have been sampled, but we could see that 860 is a relatively likely token as an example. And indeed, in our training example here, 860 does follow 91. So let's now say that we continue the process. So after 91, there's 860, we append it, and we again ask, what is the third token? Let's sample, and let's just say that it's 287, exactly as here. Let's do that again. We come back in. Now we have a sequence of 3, and we ask, what is the likely fourth token? And we sample from that and get this one. And now let's say we do it one more time. We take those 4, we sample, and we get this one. And this 13659, this is not actually 3962 as we had before. So this token is the token article instead. So viewing a single article. And so in this case, we didn't exactly reproduce the sequence that we saw here in the training data. So keep in mind that these systems are stochastic. They have, we're sampling and we're flipping coins, and sometimes we luck out and we reproduce some like small chunk of the text in the training set, but sometimes we're getting a token that was not verbatim part of any of the documents in the training data. So we're going to get sort of like remixes of the data that we saw in the training, because at every step of the way, we can flip and get a slightly different token. And then once that token makes it in, if you sample the next one and so on, you very quickly start to generate token streams that are very different from the token streams that occur in the training documents. So statistically, they will have similar properties, but they are not identical to your training data. They're kind of like inspired by the training data. And so in this case, we got a slightly different sequence. And why would we get article? You might imagine that article is a relatively likely token in the context of bar viewing single etc. And you can imagine that the word article followed this context window somewhere in the training documents to some extent, and we just happen to sample it here at that stage. So basically, inference is just predicting from these distributions one at a time. We continue feeding back tokens and getting the next one, and we're always flipping these coins. And depending on how lucky or unlucky we get, we might get very different kinds of patterns depending on how we sample from these probability distributions. So that's inference. So in most common scenarios, basically downloading the internet and tokenizing it is a pre-processing step. You do that a single time. And then once you have your token sequence, we can start training networks. And in practical cases, you would try to train many different networks of different kinds of settings and different kinds of arrangements and different kinds of sizes. And so you'd be doing a lot of neural network training. And then once you have a neural network and you train it, and you have some specific set of parameters that you're happy with, then you can take the model and you can do inference. And you can actually generate data from the model. And when you're on ChatGPT and you're talking with a model, that model is trained and has been trained by OpenAI many months ago, probably. And they have a specific set of weights that work well. And when you're talking to the model, all of that is just inference. There's no more training. Those parameters are held fixed, and you're just talking to the model, sort of. You're giving it some of the tokens, and it's kind of completing token sequences. And that's what you're seeing generated when you actually use the model on ChatGPT. So that model then just does inference alone. So let's now look at an example of
10 dakika daha doldu. Context window'u neural network'e sokuyor. Ondan sonra olası şeyler, next token'ları bulmaya çalışıyordu ya. Şimdi internal'ında aslında dediği gibi matematiksel olasılık hesapları ya da orada exponential ifadesi var. Yani matematik bilmeye gerek yok diyor ama basic calculus'u en azından ne olduğunu bilmek önem arz edebilir. Eğer detaylarını bilmeye çalışıyorsak. Burada devreye şey giriyor bakın. Parameter var ya weight. Orada mesela ChatGPT case'i için milyonlar yani ne kadar weight var seçenek milyarlardan bahsediyor. Billions of this. Burada şeye benzetiyor işte DJ'in o DJ tahtasına benzetiyor. İşte şeylerle seçeneklerle oynadığında müziğin ritmini değiştiriyor gibi. Burada değişik ritimleri yani weight'leri deneyerek gerçek ya da doğru olanını bulmaya çalışan bir şey sistem. O weight burada devreye giriyor. Zaten matematiksel formüle baktığınız zaman hem şeyin kendisi var, token'ın kendisi var, bir de yanında şey var, weight var. Ağırlığı yani. Muhtemelen mesela ChatGPT'nin API'sini ya da OpenAI'nin API'sini kullananlar varsa tam olarak emin değilim ama sadece tahmin ediyorum. Orada temperature diye bir şey vardı. Muhtemelen bununla alakalı olan bir yapı. Ama bu weight'leri bulabilmek bence önemli. ChatGPT'de mesela bazen bize bir soru sorduğumuz zaman sorunun üzerinde çok fazla iterate ettiğimizde bize şey çıkarıyor. 2 tane answer A, answer B çıkartıyor ya. Muhtemelen oradan seçtiğimiz cevaba göre de şu weight parametrelerini tekrardan gözden geçiriyor olabilirler. Sadece tahmin. Burada da bir de inference konusu var. Inference da aslında eğitilmiş modelle birlikte yeni veriler üretmek. Mesela 91 diyor Neural Network'ta işte yazı turadan bahsediyor burada olasılık olarak. Burada mesela 91'in bir sonraki ne olabilir deyip şey atıyor, yazı tura atıp 860'ı güya buldu, şanslısın falan gibisinden. Bu konteksti devamlı bu şeyden geçirip, neural netten geçirip bir sonraki seçenekleri bulmaya çalışıyor. Burada mesela şey çıkmıştı. 3962 post anlamına gelen çıkmıştı ama burada mesela article çıkmış. Yani yeni inference, yeni veri setleri oluşturabiliyorsun bununla. Eğitilmiş bir model var. Onlardan veri ürettikçe, yeni datalar ürettikçe bunlara da inference deniyor. Başka bir şey söylemiş miydim burada? Düşünüyorum. Bir de şu siteden bahsetti. Güzel de bir şeye benziyor. O hani matematiksel ifade demiştik ya. Matematiksel ifade aslında burada bu bir transformation. How to predict text. Bunu veriyor. Verdikten sonra işte bu bir sürü aşamadan geçip bir sonraki şeyi tahmin ediyor. Şurada aşağıda dur. Şöyle çekebiliyor muyum? Biraz zoom yapsam. Ya buradaki bir sonraki şeyi yapıyor. Şuradaki matematiksel hesaplamaları falan veriyor da işte yani Gerçekten şey yapmak isteyenlere, öğrenmek isteyenlere. Bir de introduction'mış yani bu arada. Tamam. Şimdi farklı bir şey söyleyecek herhalde. Devam edelim.
Training and inference that is kind of concrete and gives you a sense of what this actually looks like when these models are trained. Now, the example that I would like to work with and that I'm particularly fond of is that of OpenAI's GPT-2. So GPT stands for Generatively Pre-trained Transformer, and this is the second iteration of the GPT series by OpenAI. When you are talking to ChatGPT today, the model that is underlying all of the magic of that interaction is GPT-4, so the fourth iteration of that series. Now, GPT-2 was published in 2019 by OpenAI in this paper that I have right here. And the reason I like GPT-2 is that it is the first time that a recognizably modern stack came together. So all of the pieces of GPT-2 are recognizable today by modern standards. It's just everything has gotten bigger. Now, I'm not going to be able to go into the full details of this paper, of course, because it is a technical publication, but some of the details that I would like to highlight are as follows. GPT-2 was a transformer neural network, just like the neural networks you would work with today. It had 1.6 billion parameters, right? So these are the parameters that we looked at here. It would have 1.6 billion of them. Today, modern transformers would have a lot closer to a trillion or several hundred billion, probably. The maximum context length here was 1024 tokens. So it is when we are sampling chunks of windows of tokens from the dataset, we're never taking more than 1024 tokens. And so when you are trying to predict the next token in a sequence, you will never have more than 1024 tokens kind of in your context in order to make that prediction. Now, this is also tiny by modern standards. Today, the context lengths would be a lot closer to a couple 100,000 or maybe even a million. And so you have a lot more context, a lot more tokens in history, and you can make a lot better prediction about the next token in a sequence in that way. And finally, GPT-2 was trained on approximately 100 billion tokens. And this is also fairly small by modern standards. As I mentioned, the FineWeb dataset that we looked at here, the FineWeb dataset has 15 trillion tokens. So 100 billion is quite small. Now, I actually tried to reproduce GPT-2 for fun as part of this project called LLM.c. So you can see my write-up of doing that in this post on GitHub under the LLM.c repository. So in particular, the cost of training GPT-2 in 2019 was estimated to be approximately $40,000. But today you can do significantly better than that. And in particular, here it took about 1 day and about $600. But this wasn't even trying too hard. I think you could really bring this down to about $100 today. Now, why is it that the costs have come down so much? Well, number one, these datasets have gotten a lot better. And the way we filter them, extract them, and prepare them has gotten a lot more refined. And so the dataset is of just a lot higher quality. So that's one thing. But really the biggest difference is that our computers have gotten much faster in terms of the hardware, and we're going to look at that in a second, and also the software for running these models and really squeezing out all the speed from the hardware as it is possible. That software has also gotten much better as everyone has focused on these models and trying to run them very, very quickly. Now, I'm not going to be able to go into the full detail of this GPT-2 reproduction, and this is a long technical post, but I would like to still give you an intuitive sense for what it looks like to actually train one of these models as a researcher. Like, what are you looking at, and what does it look like? What does it feel like? So let me give you a sense of that a little bit. Okay, so this is what it looks like. Let me slide this over. So what I'm doing here is I'm training a GPT-2 model right now. And what's happening here is that every single line here, like this one, is one update to the model. So remember how here we are basically making the prediction better for every one of these tokens. and we are updating these weights or parameters of the neural net. So here, every single line is one update to the neural network, where we change its parameters by a little bit so that it is better at predicting the next token in a sequence. In particular, every single line here is improving the prediction on 1 million tokens in the training set. So we've basically taken 1 million tokens out of this data set, and we've tried to improve the prediction of that token as coming next in a sequence on all 1 million of them simultaneously. And at every single one of these steps, we are making an update to the network for that. Now, the number to watch closely is this number called loss. And the loss is a single number that is telling you how well your neural network is performing right now. And it is created so that low loss is good. So you'll see that the loss is decreasing as we make more updates to the neural net, which corresponds to making better predictions on the next token in a sequence. And so the loss is the number that you are watching as a neural network researcher. And you are kind of waiting, you're twiddling your thumbs, you're drinking coffee, and you're making sure that this looks good, so that with every update, your loss is improving and the network is getting better at prediction. Now here, you see that we are processing 1 million tokens per update. Each update takes about 7 seconds roughly. And here we are going to process a total of 32,000 steps of optimization. So 32,000 steps with 1 million tokens each is about 33 billion tokens that we are going to process. And we're currently only about 420, step 420 out of 32,000. So we are still only a bit more than 1% done, because I've only been running this for 10 or 15 minutes or something like that. Now, every 20 steps, I have configured this optimization to do inference. So what you're seeing here is the model is predicting the next token in a sequence. And so you sort of start it randomly, and then you continue plugging in the tokens. So we're running this inference step. And this is the model sort of predicting the next token in a sequence. And every time you see something appear, that's a new token. So let's just look at this, and you can see that this is not yet very coherent. And keep in mind that this is only 1% of the way through training. And so the model is not yet very good at predicting the next token in a sequence. So what comes out is actually kind of a little bit of gibberish, right? But it still has a little bit of like local coherence. So since she is mine, it's a part of the information, should discuss my father. Great companions Gordon showed me, sitting over it, and etc. So I know it doesn't look very good, but let's actually scroll up and see what it looked like when I started the optimization. So all the way here at step 1. So after 20 steps of optimization, you see that what we're getting here looks completely random. And of course, that's because the model has only had 20 updates to its parameters. And so it's giving you random text because it's a random network. And so you can see that at least in comparison to this, the model is starting to do much better. And indeed, if we waited the entire 32,000 steps, the model will have improved the point that it's actually generating fairly coherent English. And the tokens stream correctly. And they kind of make up English a lot better. So this has to run for about a day or two more now. And so at this stage, we just make sure that the loss is decreasing, everything is looking good, and we just have to wait. And now, let me turn now to the story of the computation that's required. Because of course, I'm not running this optimization on my laptop. That would be way too expensive because we have to run this neural network and we have to improve it, and we need all this data and so on. So you can't run this too well on your computer because the network is just too large. So all of this is running on a computer that is out there in the cloud. And I want to basically address the compute side of the story of training these models and what that looks like. So let's take a look. Okay, so the computer that I'm running this optimization on is this 8X-H100 node. So there are 8 H100s in a single node or a single computer. Now, I am renting this computer, and it is somewhere in the cloud. I'm not sure where it is physically, actually. The place I like to rent from is called Lambda, but there are many other companies who provide this service. So when you scroll down, you can see that they have some on-demand pricing for sort of computers that have these H100s, which are GPUs, and I'm going to show you what they look like in a second. But on-demand 8 times NVIDIA H100 GPU, this machine comes for $3 per GPU per hour. for example. So you can rent these, and then you get a machine in a cloud, and you can go in and you can train these models. And these GPUs, they look like this. So this is one H100 GPU. This is kind of what it looks like, and you slot this into your computer. And GPUs are this perfect fit for training neural networks because they are very computationally expensive, but they display a lot of parallelism in the computation. So you can have many independent workers kind of working all at the same time in solving the matrix multiplication that's under the hood of training these neural networks. So this is just one of these H100s, but actually you would put multiple of them together. So you could stack 8 of them into a single node, and then you can stack multiple nodes into an entire data center or an entire system. So when we look at a data center, can't spell. When we look at a data center, we start to see things that look like this, right? So we have one GPU goes to 8 GPUs, goes to a single system, goes to many systems. And so these are the bigger data centers, and their costs would be much, much more expensive. And what's happening is that all the big tech companies really desire these GPUs so they can train all these language models because they are so powerful. And that is fundamentally what has driven the stock price of NVIDIA to be $3.4 trillion today, as an example, and why NVIDIA has kind of exploded. So this is the gold rush. The gold rush is getting the GPUs, getting enough of them so they can all collaborate to perform this optimization. And what are they all doing? They're all collaborating to predict the next token on a dataset like the fine web dataset.
Tokenları veriyor. İşte karşıdan da bir sonraki token'ı hesaplamaya çalışıyor diye. Sonra o modelin üzerinde veri üretmeye de inference demiştik. Burada daha başka bir şeyden bahsettiğimi bilmiyorum. GPT'nin white paper'ından bahsetti. Orada teknik detaylar var. Herhalde inceler miyim bilmiyorum. Uzun da bir makaleye benziyor. Belki bakılsa iyi olabilir. Orada şu parametreler billions of this. Şimdi ChatGPT'nin ne kadardı? Ne kadar bir 100 milyar mıydı? Ya da 10 milyar mıydı? Öyle bir şeydi. Ama Fine Web'de 44 terabayt şey var. Data vardı. O da 10 trilyondu. Yani baya bir azdı. Yani aslında Fine Web'in ne kadar az bir kısmını eğittiğini düşünebilirsiniz şeyde GPT-2'de ya da GPT-4'te. Bunu yaparken, bu hesaplamayı yaparken de aslında her seferinde şu parametreleri değiştiriyor. Yani milyonlardı galiba bunu yaptı. O H100 makineler var ya, GPU makineleri, onlardan 8 tane almış. Maksimum kontrol, trained on average. Okay. Ama şeye bakmak gerekiyor. Şunu şöyle bir alayım. Neredesin? Bu LLM Visualization'da Karpathy LLM C diyeyim. Olmadı. LLM nokta C diyelim şöyle. Şu. 28.6K. Yok artık. Burada bir tane readme ya da issue açtı galiba. Bakmak gerekiyor ama bence bunun yapısını anlamak için hani modeli tekrar parametreleriyle oynayıp devam eğitiyor, update ediyor her seferinde. Orada her 20 adımda bir de inference yapıyor. Yani cümle üretiyor. İlk madde, yani ilk adımda gördüğünüz böyle saçma sapan bir şeyler üretmişti. Ama sonraki adımlarda ne kadar da böyle İngilizceyi konuşan biri gibi. Aslında öğrene bayağı bir iyi yere gelmiş. Ee, tabii bilgisayarda bunları çalıştıramıyoruz maalesef. Yani belki öyle bilgisayarınız vardır bilmiyorum ama ben de eleman dediği gibi yapıyorum aslında bu tarz şeyleri. Mesela bir videomda şey vardı, Kafka vardı. Oradaki makinelerde e, yani belki 200 GB ya da ne bileyim 96 GB'lık toplamda belki de 150 GB'lık şey vardı. Makine havuzu vardı. Cloud'dan kiralamak daha iyi. Şeyi merak ettim. Bu paid partnership mi? Karpathy tamam. Links. Yo. Şey dedi, reklam da değilmiş. Adamların şeyini vermiş, linkini. şu lambda dediği var ya, oradan kendine bir tane GPU, 8 tane aslında bir tane nodun içinde 8 tane o H100'lerden çalışıyor. Ve dediğine göre 2 gün boyunca orada çalışacak ve en sonunda ona sonucu verecek, ne olduğunu verecek. Sonra sen ona bir soru soracaksın. Yani token, konteksti vereceksin. O da sana karşılığında cevabını vermiş olacak. Hocam koskoca Andrej Karpathy'ye eleman dediniz. Ya eleman diyor, saygısızlığımızdan değil ya. Bazen unutuyorum. Beklememek adına eleman diyorum. Ben de seviyorum kendisini. Yani videoları falan anlaşılır. Benim kafadan.
This is the computational workflow that basically is extremely expensive. The more GPUs you have, the more tokens you can try to predict and improve on, and you're going to process this data set faster, and you can iterate faster and get a bigger network and train a bigger network and so on. So this is what all those machines are doing, and this is why all of this is such a big deal. And for example, this is a article from like about a month ago or so. This is why it's a big deal that, for example, Elon Musk is getting 100,000 GPUs in a single data center. And all of these GPUs are extremely expensive, are going to take a ton of power, and all of them are just trying to predict the next token in the sequence.
Abi 100.000 GPU bikini giydirmek için.
And improve the network by doing so. And get probably a lot more coherent text than what we're seeing here a lot faster. Okay, so unfortunately, I do not have a couple 10 or 100 million of dollars to spend on training a really big model like this. But luckily, we can turn to some big tech companies who train these models routinely and release some of them once they are done training. So they've spent a huge amount of compute to train this network, and they release the network at the end of the optimization. So it's very useful because they've done a lot of compute for that. So there are many companies who train these models routinely, but actually not many of them release these what's called base models. So the model that comes out at the end here is what's called a base model. What is a base model? It's a token simulator, right? It's an internet text token simulator. And so that is not by itself useful yet, because what we want is what's called an assistant. We want to ask questions and have it respond to answers. These models won't do that. They just create sort of remixes of the internet. They dream internet pages. So the base models are not very often released because they're kind of just only a step one of a few other steps that we still need to take to get an assistant. However, a few releases have been made. So as an example, the GPT-2 model released the 1.5 billion model back in 2019. And this GPT-2 model is a base model. Now, what is a model release? What does it look like to release these models? So this is the GPT-2 repository on GitHub. Well, you need two things basically to release model. Number one, we need the Python code, usually, that describes the sequence of operations in detail that they make in their model. So if you remember back this transformer, the sequence of steps that are taken here in this neural network is what is being described by this code. So this code is sort of implementing the what's called forward pass of this neural network. So we need the specific details of exactly how they wired up that neural network. So this is just computer code, and it's usually just a couple hundred lines of code. It's not that crazy, and this is all fairly understandable and usually fairly standard. What's not standard are the parameters. That's where the actual value is. What are the parameters of this neural network? Because there's 1.6 billion of them, and we need the correct setting, or a really good setting. And so that's why, in addition to this source code, they release the parameters, which in this case is roughly 1.5 billion parameters. And these are just numbers. So it's one single list of 1.5 billion numbers, the precise and good setting of all the knobs such that the tokens come out well. So you need those two things to get a base model.
Şimdi o modellerin yanındaki parametreleri öğrenmişsinizdir, artık ortamlarda satarsınız. Var ya 7.2 billion, 64 billion falan.
Release. Now, GPT-2 was released, but that's actually a fairly old model, as I mentioned. So actually the model we're going to turn to is called Llama 3. And that's the one that I would like to show you next. So Llama 3, so GPT-2 again was 1.6 billion parameters trained on 100 billion tokens. Llama 3 is a much bigger model and much more modern model. It is released and trained by Meta. and it is a 405 billion parameter model trained on 15 trillion tokens. In very much the same way, just much, much bigger. And Meta has also made a release of Llama 3, and that was part of this paper. So with this paper that goes into a lot of detail, the biggest base model that they released is the Llama 3.1 405 billion parameter model. So this is the base model. And then in addition to the base model, you see here, foreshadowing for later sections of the video, they also released the instruct model. And the instruct means that this is an assistant. You can ask it questions and it will give you answers. We still have yet to cover that part later. For now, let's just look at this base model, this token simulator, and let's play with it and try to think about, what is this thing and how does it work, and what do we get at the end of this optimization if you let this run until the end for a very big neural network on a lot of data. So my favorite place to interact with the base models is this company called Hyperbolic, which is basically serving the base model of the 405B Llama 3.1. So when you go into the website, and I think you may have to register and so on, make sure that in the models, make sure that you are using Llama 3.1 405 billion base. It must be the base model. And then here, let's say the max tokens is how many tokens we're going to be generating. So let's just decrease this to be a bit less, just so we don't waste compute. We just want the next 128 tokens and leave the other stuff alone. I'm not going to go into the full detail here. Now, fundamentally, what's going to happen here is identical to what happens here during inference for us. So this is just going to continue the token sequence of whatever prefix you're going to give it. So I want to first show you that this model here is not yet an assistant. So you can't, for example, ask it, what is 2 plus 2? It's not going to tell you, oh, it's 4. What else can I help you with? It's not going to do that. Because what is 2 plus 2 is going to be tokenized, and then those tokens just act as a prefix. And then what the model is going to do now is just going to get the probability for the next token, and it's just a glorified autocomplete. It's a very, very expensive autocomplete of what comes next, depending on the statistics of what it saw in its training documents, which are basically web pages. So let's just hit enter to see what tokens it comes up with as a continuation. Okay, so here it kind of actually answered the question and started to go off into some philosophical territory. Let's try it again. So let me copy and paste, and let's try again from scratch. What is 2 plus 2? So, okay, so it just goes off again. So notice one more thing that I want to stress is that the system, I think every time you put it in, it just kind of starts from scratch. So it doesn't, the system here is stochastic. So for the same prefix of tokens, we're always getting a different answer. And the reason for that is that we get this probability distribution and we sample from it, and we always get different samples, and we sort of always go into a different territory afterwards. So here in this case, I don't know what this is. Let's try one more time. So it just continues on. So it's just doing the stuff that it saw on the internet, right? And it's just kind of like regurgitating those statistical patterns. So first things, it's not an assistant yet. It's a token autocomplete. And second, it is a stochastic system. Now, the crucial thing is that even though this model is not yet by itself very useful for a lot of applications just yet, it is still very useful because in the task of predicting the next token in the sequence, the model has learned a lot about the world, and it has stored all that knowledge in the parameters of the network. So remember that our text looked like this, right? Internet web pages. And now all of this
Yok ama bu bizim ya da Karpathy'nin eğitmeye çalıştığı modeli tabii günler sürüyor ama bu modelleri büyük şirketler kendi devasa compute sistemlerinde düzenli olarak eğitiyorlar. İşte o gördüğün Llamalar, Mistral'ler, bilmem neler falan büyük şirketler onları eğitiyor ve bir yerde hizmete sunuyor. Mesela lokalinizde Ollama diye bir tool var. Onu kullanabilirsin. Bu machine learning modellerini lokalinde çalıştırabilmek adına. Onların değişik parametreleri var. İşte 7 bilyon olan, 14 bilyon, 60 sayısını hatırlamıyorum. Belki 70-80 olabilir. En son gösterdiği 11 ay önceki olan 405 bilyon parametre. Yani o weight'ler vardı ya, o 405 milyar parametreli seçeneği Llama 3 modeli 3.1. Bunu mesela GitHub'da yayınlıyorlar. Yayınladıktan sonra içine baktığınızda işte bunu nasıl parametrelerin ne olduğunu, nasıl inference ettiğini falan Python kodunda gösteriyor olması lazımından bahsetti. Muhtemelen siz de incelemek isterseniz eğer nasıl yapıldığıyla alakalı bir script buluyor olmanız lazım o repoda. O modellerde bir de Lama'nın da aslında okuması gereken white paper'ların sayısı artıyor. Lama'nın da mesela yayınladığı bir normal model bir de instruct modeli var. Instruct modelleri soru cevap yapabiliyorsun. Soru soruyorsun cevap veriyor ama diğerleri ise sadece inference yapıyor. Token'ı veriyorsun bir sonrakini autocomplete gibi çalıştırıyor. Ama instruct'larda soru cevap. Instruct olmayanları nerede kullanıyoruz mesela? Coding agent'larda kullanılıyor değil mi? Şöyle az önce bahsettiğim aracın adı şuydu. Ollama diye bir tane araç var. Bak şu. Burada mesela modellere baktığın zaman modellerin içinde bir sürü model var. Burada yenileri falan da geliyor. Ve yapabiliyorsun. Ee, Bunları filtreleyebiliyorsun şeye göre. Mesela Llama 3.2. Llama 3.2'ye bakalım. Burada serve ettiği mesela ne var? 1 bilyon parametreli, 3 bilyon parametreli olan var burada. Başka böyle büyük şeyli olan yok mu? Mesela bak şu 3.1'miş o 2'de yapmamış onu tamam. Bak 405 parametre buradaymış. Size'ı 243 GB'mış arkadaşlar. 243 GB. Modelin büyüklüğü. Yani ciddi bir sisteminiz oluyor olması lazım bunun için. Burada da evaluation'lardan bahsediyor. Bakabilirsiniz yani Llama ile ChatGPT'nin karşılaştırılması. Ne kadar loss var bilmem ne var diye. Tamam. Başka burada bahsettiği Lama'dan bahsetti. Bir de o hyperbolical vardı ya modele soru sordu cevap verdi. Orada vardı soruyu soruyor cevap veriyor her seferinde farklı şeyler cevap veriyor. Onun sebebi de context window verdiğin zaman bir sonraki token'ı hesaplıyordu ya. Orası olasılıksal olduğu için her seferinde farklı cevaplar üretiyor. Ondan bahsediyordu. Şimdi son 10 dakikalık batch'i de izleyelim.
This is sort of compressed in the weights of the network. So you can think of these 405 billion parameters as a kind of compression of the internet. You can think of the 405 billion parameters as kind of like a zip file, but it's not a lossless compression, it's a loss C compression. We're kind of like left with kind of a gestalt of the internet, and we can generate from it, right? Now, we can elicit some of this knowledge by prompting the base model accordingly. So, for example, here's a prompt that might work to elicit some of that knowledge that's hiding in the parameters. Here's my top 10 list of the top landmarks to see in Paris. And I'm doing it this way because I'm trying to prime the model to now continue this list. So let's see if that works when I press enter. Okay. So you see that it started the list and it's now kind of giving me some of those landmarks. And now notice that it's trying to give a lot of information here. Now, you might not be able to actually fully trust some of the information here. Remember that this is all just a recollection of some of the internet documents. And so the things that occur very frequently in the internet data are probably more likely to be remembered correctly compared to things that happen very infrequently. So you can't fully trust some of the things that and some of the information that is here because it's all just a vague recollection of internet documents. Because the information is not stored explicitly in any of the parameters. It's all just the recollection. That said, we did get something that is probably approximately correct, and I don't actually have the expertise to verify that this is roughly correct. But you see that we've elicited a lot of the knowledge of the model. And this knowledge is not precise and exact. This knowledge is vague and probabilistic and statistical. And the kinds of things that occur often are the kinds of things that are more likely to be remembered in the model. Now, I want to show you a few more examples of this model's behavior. The first thing I want to show you is this example. I went to the Wikipedia page for zebra, and let me just copy paste the first even one sentence here. And let me put it here. Now, when I click enter, what kind of completion are we going to get? So let me just hit enter. There are 3 living species, etc., etc. What the model is producing here is an exact regurgitation of this Wikipedia entry. It is reciting this Wikipedia entry purely from memory, and this memory is stored in its parameters. And so it is possible that at some point in these 512 tokens, the model will stray away from the Wikipedia entry. But you can see that it has huge chunks of it memorized here. Let me see, for example, if this sentence occurs by now. Okay, so so we're still on track. Let me check here. Okay, we're still on track. It will eventually stray away. Okay, so this thing is just recited to a very large extent. It will eventually deviate because it won't be able to remember exactly. Now, the reason that this happens is because these models can be extremely good at memorization. And usually this is not what you want in the final model, and this is something called regurgitation, and it's usually undesirable to cite things directly that you have trained on. Now, the reason that this happens actually is because for a lot of documents, like for example Wikipedia, when these documents are deemed to be of very high quality as a source, like for example Wikipedia, it is very often the case that when you train the model, you will preferentially sample from those sources. So basically the model has probably done a few epochs on this data, meaning that it has seen this web page like maybe probably 10 times or so. And it's a bit like you, like when you read some kind of a text many, many times, say you read something 100 times, then you will be able to recite it. And it's very similar for this model. If it sees something way too often, it's going to be able to recite it later from memory. Except these models can be a lot more efficient, like per presentation than a human. So probably it's only seen this Wikipedia entry 10 times, but basically it has remembered this article exactly in its parameters. Okay, the next thing I want to show you is something that the model has definitely not seen during its training. So for example, if we go to the paper and then we navigate to the pre-training data, we'll see here that the data set has a knowledge cutoff until the end of 2023. So it will not have seen documents after this point. And certainly it has not seen anything about the 2024 election and how it turned out. Now, if we prime the model with the tokens from the future, it will continue the token sequence and it will just take its best guess according to the knowledge that it has in its own parameters. So let's take a look at what that could look like. So the Republican Party ticket, Trump, okay, President of the United States from 2017. And let's see what it says after this point. So for example, the model will have to guess at the running mate and who it's against, etc. So let's hit enter. So here are things that Mike Pence was the running mate instead of JD Vance. And the ticket was against Hillary Clinton and Tim Kaine. So this is kind of an interesting parallel universe potentially of what could have happened according to the LLM. Let's get a different sample. So the identical prompt, and let's resample. So here the running mate was Ron DeSantis, and they ran against Joe Biden and Kamala Harris. So this is again a different parallel universe. So the model will take educated guesses, and it will continue the token sequence based on its knowledge. And it will just kind of like, all of what we're seeing here is what's called hallucination. The model is just taking its best guess in a probabilistic manner. The next thing I would like to show you is that even though this is a base model and not yet an assistant model, it can still be utilized in practical applications if you are clever with your prompt design. So here's something that we would call a few-shot prompt. So what it is here is that I have 10 words, or 10 pairs, and each pair is a word of English, colon, and then the translation in Korean. And we have 10 of them. And what the model does here is at the end we have teacher, colon, and then here's where we're going to do a completion of, say, just 5 tokens. And these models have what we call in-context learning abilities. And what that's referring to is that as it is reading this context, it is learning sort of in place that there's some kind of an algorithmic pattern going on in my data. And it knows to continue that pattern. And this is called kind of like in-context learning. So it takes on the role of a translator. And when we hit completion, we see that the teacher translation is 선생님, which is correct. And so this is how you can build apps by being clever with your prompting, even though we still just have a base model for now. And it relies on what we call this in-context learning ability, and it is done by constructing what's called a few-shot prompt. Okay, and finally, I want to show you that there is a clever way to actually instantiate a whole language model assistant just by prompting. And the trick to it is that we're going to structure a prompt to look like a web page that is a conversation between a helpful AI assistant and a human. And then the model will continue that conversation. So actually, to write the prompt, I turned to ChatGPT itself, which is kind of meta, but I told it, I want to create an LLM assistant, but all I have is the base model. So can you please write my prompt? And this is what it came up with, which is actually quite good. So here's a conversation between an AI assistant and a human. The AI assistant is knowledgeable, helpful, capable of answering a wide variety of questions, etc. And then here, it's not enough to just give it a sort of description. It works much better if you create this few-shot prompt. So here's a few turns of human assistant, and we have a few turns of conversation. And then here at the end is we're going to be putting the actual query that we like. So let me copy paste this into the base model prompt. And now let me do human column. And this is where we put our actual prompt. Why is the sky blue? And let's run. Assistant. The sky appears blue due to the phenomenon called ray light scattering, etc., etc. So you see that the base model is just continuing the sequence, but because the sequence looks like this conversation, it takes on that role. But it is a little subtle because here it just, it ends the assistant and then just, hallucinates the next question by the human, etc. So it'll just continue going on and on. But you can see that we have sort of accomplished the task. And if you just took this, why is the sky blue? And if we just refresh this and put it here, then of course we don't expect this to work with a base model, right? We're just gonna, who knows what we're gonna get? Okay, we're just gonna get more questions. Okay, so this is one way to create an assistant, even though you may only have a base model. Okay, so this is the kind of brief summary of the things we talked about over the last few minutes. Now, let me zoom out here. And this is kind of like what we've talked about so far. We wish to train LLM assistants like ChatGPT. We've discussed the first stage of that, which is the pre-training stage. And we saw that really what it comes down to is we take internet documents, we break them up into these tokens, these atoms of little text chunks, and then we predict token sequences using neural networks. The output of this entire stage is this base model. It is the setting of the parameters of this network. And this base model is basically an internet document simulator on the token level. So it can just, it can generate token sequences that have the same kind of like statistics as internet documents. And we saw that we can use it in some applications, but we actually need to do better. We want an assistant. We want to be able to ask questions and we want the model to give us answers. And so we need to now go into the second stage, which is called the post-training stage. So we take our base model, our internet document simulator, and hand it off to post-training. So we're now going to discuss a few.
Bence iyi şey yaptık. Zaten buradaki özetini verdi. Ama en sonunda baktığında bir sistem promptundan bahsetti değil mi? Sistem promptu vererek sorduğunda farklı cevap veriyor ama normal düz sorduğunda bambaşka cevap veriyor. Birbirleriyle ilişkili ama şey değil. Bir de modellerde ne kadar up to date olduğuna bakmak için Wikipedia'dan birkaç tane örnek alıp sordu. Birebir aynı cevabı verdi. Çünkü o parametre'larda memory olabiliyor. Varsa kendinde öyle bir doküman oradan cevap veriyor. Ama hiç indekslemediği ya da eğitilmediği data üzerinden bir şey sorduğunda tahmin etmeye çalışıyor. Mesela 2024 Amerika seçimlerinden soru sordu. Sanki paralel evrendeymiş gibi cevap vermişti ona. Öyle bir durum. Şimdi post training'e bakacak ama onu bir sonraki şeyde bakalım. Hepsini bir anda sindirmeyelim yani.